Hi everybody, I'm Vint Cerf, and I took my jacket off because I'm in Palo Alto and it's hotter than Hades here, even though I'm, to be honest, in an air-conditioned room. So I'm not uncomfortable. And I've consumed the 6 minutes of your time by hacking around trying to get online. So I don't want to waste it by telling you all of the amazing prizes and awards that our speaker, Lara Suzuki, has won. But I can tell you, I've been astonished and impressed and happy to see that she's been honored many times in the UK and elsewhere and here at Google for her work, which is heavily influenced by artificial intelligence and machine learning today as part of our Office of the Chief Technology Officer of our Google Cloud platform. Today, Lara is going to show us how we can make use of machine learning in space-based applications running over delay and disruption tolerant networks. And I'm assuming that most of you on this call are very familiar with DTN and the work that's been going on in the IPNSIG and the project working group within which Lara is participating. She's also working with the JPL with the team there. So without further ado, Lara, I'd like to ask you to tell us more about how we can make use of machine learning in space-based applications, particularly given that the latencies are very high and local processing may turn out to be extremely valuable to avoid trying to ping pong back and forth between distant planets and our Earth-based resources. So over to you, Lara.
Thank you so much, Vint. Thank you everyone for joining here. I am going to be talking to you guys today about how we can enable space exploration by using AI, also to pursue amazing science applications, but also to improve the data communications in space. And throughout the presentation, I'm going to reference some of the relevant aspects of DTN and how we can adapt AI systems to work on top of DTN. Before I get into more of the details, I would like to give a kind of quick intro into the AI history. So in the 14th century, we had William of Ockham. He was a 14th century friar and philosopher, and he loved simplicity. And he believed that scientists should prefer simpler formulas or theories over more complex ones. And the less complex a machine learning model is, the more likely that a good empirical result is not just due to the peculiarities of the sample. And as we moved to the 1950s, we had a generation of mathematicians, scientists, and philosophers. We had Alan Turing publishing a paper speculating about the creation of machines that think. We had Ada Lovelace. The first algorithm was written by her for a machine to solve. And we had also John McCarthy, who coined the term artificial intelligence in a conference in Dartmouth. After a while, we reached a period of AI winter, where we had like financial setbacks that was dampened by this initial set of optimism due to limited computer power, intractability of solving problems in an exponential time. But during the 90s, we had advancements in microprocessors, computers, data storage, and data transfer, which addressed the earlier concerns about speed, computational costs, and information requirement. So in 1997, we had IBM Deep Blue defeating Kasparov in the world champion at chess. Then we had IBM Watson winning Jeopardy game. And in 2017, we saw Google AlphaGo defeating the world winner on the game of Go. So the memory and speed of computers just caught up with what we could do with AI. And big data and massive computing allow us to train amazing models to create deeper and more specialized application. And what we are going to see is that throughout the time, we're going to see advancements in computer science, mathematics, and neuroscience as well. And what we noticed is that we have seen change and improvements in many areas of AI, particularly in vision, in language, in translation, and in speech recognition and speech to text as well. And also in events, that is like events triggered machine learning, triggering different functions and applications for users to consume on the edge and also in computers. And when we look at this, the same technology that knows if something we are seeing as a cat or a dog is also the technology that is empowering us to cure cancer and to do astonishing applications to help to solve like the most pressuring issues that we have in mankind today. And we have seen many applications in the field in industry. So we have seen applications in inspection using vision AI for us to inspect and detect whether we have a faulty system somewhere. We have seen advancements in precision manufacturing and precision medicine as well in healthcare and retail, robotics, and agriculture. And now we are seeing a lot of things like AI in space. We have seen before, but now we are seeing like a lot of like more advancements in AI applied to space research. I'm going to drive you through some of the ideas and key concepts of the work I've been doing on AI applied to space research. What I'm going to be covering here is everything that I developed and deployed over a DTN architecture. So I have different nodes across the globe in Europe, in Australia, in the United States, and also in the UK. And I also have a collection of Raspberry Pis running as well, collecting data using different protocols and interacting through a contact plan, enabling like multicasting. So all the data I'm going to show here might be running on a particular server and propagating all the changes and the requests and the results to other members of the network here. So the first thing I wanted to share with you, like, is one example that I'm not going to go into detail here, but what you can see in the IPNSIG presentation is anomaly detection, but used in a context of processing real-time data to enable us to get actionable results online and collecting AI telling us whether there's an anomaly on a system or not. And that is quite useful for us to detect if something is wrong with a rocket, with a satellite, that also enable us to collect data in real time and also act in real time. And that is kind of a processing tabular data, that is data in numerical form that might be collected in batch or in real time. One example that I would like to share with you guys here is about predicting a classification of stars. So in astronomy, stellar classification is the classification of stars based on the spectral characteristics. And the classification scheme of galaxies, quasars, and stars is one of the most fundamental things we do in astronomy. And the early cataloging of stars and their distribution in the sky has led to the understanding that they make up our own galaxy. And following the distinction of that Andromeda was a separate galaxy to our own, and numerous galaxies began to be surveyed and more powerful telescopes were built. And the data set that I got was a data set created by Sloan Digital Sky Survey. And this data set consists of 100,000 rows of information about like sampling data. And it helps us to classify whether an object we are observing in space it might be a star, a galaxy, or a quasar based on their spectral characteristics. And so the data set that I got, again, is like 100,000 observation of space, and each observation is described by 17 feature columns and one class column that we want to classify whether that is a star, galaxy, or quasar. And for instance, we have object identifier. So in here, I don't know if you guys can see my mouse here, but if you see at the top, this is the explainability. This table is the explainability of the data, of the input data that I got for this model. And we see that redshift, that is like the value based on the increasing wavelength. If you guys wanted to search this for the ones who doesn't know it. So our redshift reveals how an object in space, star, planet, or galaxy is moving compared to us. So it is the parameter that mostly explain our model. And also parameters such as infrared filter in the photometric system. We also have parameters like the G parameter is the green filter in the photometric system. I can share with you guys the details of this data. But the idea that I got in here was to use transfer learning. That is the idea that we can train a deep neural network. And from that deep neural network, we can repeat the same kind of architecture to create a machine learning predictions in a space that we can do a neural architecture search. So the basic idea is for us to define our data, analyze the input of features to select the ones that mostly explain our system, to train our model, perform feature engineering, model selection, and hyperparameter tuning. So we use a technique called neural architecture search, and we evaluate the model behavior and select the model and the architecture that will provide the best predictions for us. So I run a model on Google Cloud, and for the true labels here, if you see these confusion matrix at the bottom, we have the classifications for galaxy, star, and quasar. And then you can see that I managed to get some very good results for them. And the ones that I can get some improvement is the last one that is about quasars. And I wanted to show you guys a little bit about how this kind of can work in practice. So I'm just gonna switch here to a different tab here. So if you remember for the example that I showed you about the prediction of like temperature of the AstroPi sensor, so we can have like a notebook and then we can run and code an artificial neural network representing data in feature layers, building a deep neural network and run our model here. And by the way, all this code is available on my GitHub repo, so you guys can find this later. But what we do here is that we call the functions for us to train our model, and then after running the model, we can have some representation of how well the model performed. But then we have our model, and what we can do with a stellar classification is actually go into an endpoint and actually make an API call to try to get the results of the model back to us in the way that we were predicting before. And if I kind of make some of the data here, so I'm going to just configure an endpoint here. So I'm going to configure my endpoint, my project ID, and my data file. And then if I show you the data that I'm going to use to call an API to get the real-time prediction. So if you see here, we have an instance for a prediction. So this is all the data that I have collected about a particular stellar object. And so I have the redshift parameter and all the other parameters that I can use here. And I just make a call to an API here, passing those parameters, and I can get the prediction coming to me back in real time. Let's hope it's going to run. Let me just get authorization. Oh, sorry, guys, that expired. Now I have to run that again. Yeah, so this is the predictions I got. So those are the scores that I got in real time. So at the time I saw an object, I can send the JSON file or any other kind of file to an endpoint using DTN, and I can get the scores for the predictions I have made. So for instance, for the classes for a galaxy, the object I just submitted is 94% chance of being a galaxy. And for being a star is really very remote possibility, and also a quasar is also very remote possibility for that. But this is an idea for us to not only run the model, but also use like REST endpoints for us to do real-time predictions when we are doing like application for, especially on top of DTN, that we can just pass some configuration file. But what I have just shown to you just talks about the ML code. And the ML code has to be expanded into several steps of a workflow for us to really productionize and make this meaningful for us and create, for instance, that endpoint that I just created. And the challenge is, especially as the number and complexity of our input column increases, we hit a combinatorial explosion of things for us to worry about. And this is just an example of the things that we have to worry about. We have to worry about the data preparation. We have to handle, for instance, outliers, missing values, imbalanced data, because we have to make sure all the classes that we have a balanced representation. Otherwise, we're going to have bias and classify some objects much better than others. We have to do the feature engineering to encode the data that we collect in a proper way. We have to select our architecture. So in this example of the stellar classification, I had to use a neural architecture search that I looked through an entire body of architectures and find which one is the best one. And also parameter selection. We have to fine tune our model to not overfit, to not learn too much about the data it's saying so it can generalize much well. We also have to identify our tuning strategy and also evaluate our model. We have to evaluate our data because if the distribution and the shape of the data kind of changes, we are going to have to consider maybe potentially a different model. And we have to look at changes in the feature level and also evaluation at the prediction level. That is like the outputs I'm getting. Are they really meaningful? And we have to rinse and repeat up to a lot of times, like tens and several times during one single use case. And that's why approaches using, for instance, cloud computing or using transfer learning is really helpful for us, because all this thing for us to productionize our model, for instance, from the ML code to look for configuration, server infrastructure, our data collection, feature extraction, all those components here, they can be taken care of from us. And we don't need to worry much about them, because if one of those components, they die, we can get those spinned back up immediately based on configuration files. So we don't need to worry too much about the underlying infrastructure. Otherwise, of course, we have to know about them. If we know like our model is going to consume a lot of memory, we have to prepare different kind of setup for this. But we have to be mindful that doing the ML code is just a tiny proportion of the work that is coming up. And when we think about architecture selection of ML models, there are many techniques here, and I'm putting here a link to a paper that is quite interesting, that is like to explore a neural network architecture. And the basic idea is that we have a sample architecture A with a probability P, and we can train a child network with architecture A to get accuracy R. And we compute the gradient of P to scale it by R to update the controller so that we can identify what is the best architecture for us. And in this example here on the side, you can see the first architecture here was created by a human, was generated by a human. And the other architecture selection here was generated by a computer that could go through a space of options, identify what is the activation function for my particular model, what are the number of layers that I have to have. So we see that the space of possibilities are much well explored when we make use of techniques such as like transfer learning. And when we also work with deep neural network, we also have to understand a little bit more about the feature extraction and the prediction output. When we work with like feature extraction, we look in a deep neural network. Each layer of our neural network will take care of, for instance, identifying the edges, the shapes, objects, identify whether something's a hot dog or not a hot dog, for instance, identify complex objects like textures. And in the classification part is where we can kind of just tweak that part for the model for the application we are defining at the end. And all the activation functions, all the things intrinsic to the neural architecture search might not have to be changed depending on the use case that you are working with. And that is especially applicable to the next use case that I'm going to be talking to you guys about, that is like object classification. So object detection is more appropriate for us to identify relevant objects that is in a single image or in a video, because in video we process the different frames of the video, and then we can make classifications on this. And when we look at the object detection, it is at the same time a regression and a classification task. So when we think about regression, it is the intersection over union area. So that corresponds to the overlapping area between the predicted box and the ground truth box. So that is going to be between 0 and 1, so the higher the better. And it can also be a classification task. So we take the mean average precision, and that is computed over all the classes of the data set. So we can identify what we are talking about and then segment the object that we are interested in. And there are many algorithms for us to work with object classification, but a special type of algorithm is called convolutional neural networks. And they are commonly used in applications like object recognition and voice recognition, where the input has local structure and also has symmetry. So for example, if you consider the task of labeling regions in an input image, so the inputs are pixels in the image. So every single pixel or a voxel, if you're working on a 3D with a volumetric image. And there's interaction between the pixels because those close together are likely to share the same label, like because of the local structure. So for example, if one pixel is grass on a particular image, then the probability that the ones around it are grass too, and compared to a pixel much further away. And there's also symmetry because the same type of region looks similar regardless of where it is in the image. For instance, if we see a person in one part of the image, that might look similar to another person somewhere else in the image. So the convolutional neural networks are useful in these situations because they capture the local interactions between components and the input by, the first thing we do here is we use a weighted average to combine a window of locally close inputs, as I described with the example of the person. And we use the same set of weights for each window of inputs. So this weighted combination is called convolution. That's why we call convolutional neural nets. And the hidden unit that performs this hidden unit, this hidden part, is often called a convolutional layer. And a convolutional neural network is some combination of those convolutional layers. As I showed you in that example, that we have those deep neural networks of layers of networks. And in object classification, we have many algorithms available. So I linked here some papers for you guys to take a look into. But one of the top one that is being widely used is the faster convolutional neural network that is based on region proposal network, and that reduces the compute intensity. So it's much more efficient in terms of computational resources. So when we look into this algorithm, we can see this as a region-based convolutional network, and that works based on 3 simple steps. So first of all, we use just one convolutional neural network for the entire image instead of like 2,000 types of a convolutional neural networks as other models they use. So we just use one for the entire image. So we scan this input image for possible objects using an algorithm called selective search. And we create a set of region proposals. Then we can run a convolutional neural net on top of each of those region proposals, and that will give us an output of each of those convolutional neural network and feed into. And we're going to have a support vector machine to classify the region, and a linear regressor to tighten the bounding box of the object if such an object exists. So that box that we see around an object to delimiter, to serve a box to really say what is in this region is the object that you are interested in, or is what I could find on this image. And the closer that box is to the object, the more accurate it is. Otherwise, we're going to you have a box this big and just a tiny person in the middle. And I run an example here for crater detection, and I want to show that to you guys and run an example here with you guys. So the idea, if you look into, it's my left, you can see like the first image that you can see like with the 0, 100, 200. So that the first one, we have humans labeling that image, putting in there where that crater is located. So we have like different craters like detected here. And then the second image, I'm going to explain that to you guys. So when I run the examples, we can understand what is going on. So when we look into this image, we see that everything that is in blue is the label, the value selected by the human. And everything that is in red is what has been selected by the machine learning algorithm, by the convolutional neural network. So we can, by looking into those images, we can see how precise we are being in detecting something and losing or missing something that we couldn't see before. So I'm going to run the crater detection example here. So this is an example of the data that I can see on the data set. So for instance, we have data here that we have nothing, no crater at all. And then so we don't have any marks that it has been labeled. So we have one other one that we had something marked in there as there's a crater or there's not a crater here. And we have another one with tons of examples like it with the crater images. And I have my code here that again is going to be available on my GitHub. And here I'm defining like how many times I want to run this to make sure that we can have a good learning of what it is that I see on the image. And I have two classes here that is like, it's a crater, not a crater. And so if we go to, so I trained this model for about like 2 hours for me to be able to get kind of some good results. And I'm just gonna run some of them now. Okay. So in here, I have, for instance, the example, you see like we still miss some of the labels. So for instance, here on the top, you can see on the first like part of the top, we see that we have the red that was detected by the machine learning model and the blue that was the label by the human. And we see there's a blue label here that a human marked as being a crater, but the machine learning algorithm couldn't guess that. But we also have some other places here that we have like craters detected. You see the boxes that are in red. That the crater was detected here by the machine learning algorithm, but not by the human. And that is why it's so important for us to have the human in the loop, because what a human can do here is actually say, and tell the machine learning, okay, this area, yeah, you are right, there was a crater there and I missed it. So we can relabel that data, or even tell the machine learning algorithm, you told this is a crater, but that is not a crater. So that serves as a new example for you to keep improving the performance of your model and how we are detecting better images and better outcomes. So we have a variety of examples here. So in here, we can see at the end of the image, we see that the algorithm detected like, for instance, a crater. If you see like a very tiny box here, but the machine learning, but the human didn't take that one. But we have some fun examples here. So for instance, this one, there was a huge crater here. And then we couldn't get much of the ones that were outside, for instance, that didn't have like the craters were not too deep in comparison to the others. So if we run this model a little bit more and tune the learning rate or some other aspects of the neural network, we might be able to learn a little bit more. We also have some weird stuff going on here. So for instance, this blue circle here is a kind of like a false positive by a human, I think, but it's not like there's really nothing there for me to see. But there's a very fun example here I'm going to show you. So in here, we see that we missed a lot of labels here. There was not a very good performance on this one. But again, we have to have a human to go and help us to detect. But I want to show you, for instance, so we have a big crater here. We could detect it. We could detect this other one. Yeah, so this is an example here. So it's a quarter of a crater here. If you see like it was a crater formed by 4 parts. And the human labeled is as a crater, but we might not have that many examples of craters looking like this that are partially displayed. That's why we could get something a little bit tiny there, if you see that red box there, but not the entire crater because it's shown partially. So that is why I said to you, the more examples we have showing the diversity of kind of images, the better our algorithm is going to run and perform. So for instance, the different types of textures, the different types of sizes, and also the depth of the craters is quite important for us to have a very good and healthy kind of database with all those examples. So This was like the example of us like using a convolutional neural network for this, but using the faster model for us to be able to save on computation. But one of the things we think about, like if we are in space and collecting all that amount of data, how can we transfer this over DTN? Watch the lecture I gave on IPNSIG so you can see the simulation of this kind of running. But one of the things that I'm using now is federated learning and analytics over DTN to allow us to process data on the edge and don't transfer that amount of data to Earth, where we have a lot of computing power to process all that information. So DTN is what I call DTN-ML. So DTN-ML is catered to run in environments where we have intermittent connectivity, we have variable delays, high bit error rates, and asymmetric and simplex links. So that rings a bell, right? So we are talking about DTN. I'm going to show it to you guys here, like a basic idea of how the algorithm works. The first thing we do is, for us to get started with this, we have to train and evaluate on some proxy data or like historical data or some data, even like starting with nothing if we have not seen anything before. So this is an example of a server that we have here on cloud, and we have a mission operator here. And this tiny database in yellow here, that is the SDR. And we also have our contact graphs here working with those satellites, that rocket, and also that rover here. And I put the IPN number here and also the multicasting channel that those satellites and relays, they're talking to each other. And if you see here behind Mars, we have like a rocket or something that is not accessible to the network at that point. So let's see how that runs. So we train firstly our model and evaluate the zone of proxy data. Once we have a decent model, we can then propagate this to all the nodes of the network. And the nodes of the network will be performing a task that are similar. So they have to be doing like a collective task, something that is equal to all of them. So they might be like, for instance, looking for like stars or something. So we look into our model and we train on local data. So we leave the data on the edge and we train there. So instead of passing on the images that those satellites and those devices they collect in space, we just pass the model updates. So the matrix with the weights of our machine learning model, and we pass that is very lightweight, and we pass this to a central aggregator that would then aggregate those updates, find which models to take into account to consider for this, aggregate them, and produce a much better model, because then those devices, they can learn together. Because if they have not seen some type of like star, for instance, they might learn from another one that has seen that before. So we have that new model version created, and then that process we repeat. So we propagate this to them, and then we're going to have a configuration file dictating how often we have to retrain the model. And if a model is retrained, but the performance is not as good as it was before, we do not participate in the cohort of the federated learning. So we don't take part in it. And so this is an example that I run using DTN-ML. So the idea here was to say, what is in this image here? And this image here is about like, if we see like the ion event here, so we start reading here, we say we see water and 97% of certainty, I saw water, I see a tropical cyclone, I see, for instance, cloud. And if you see the image on the other side, the yellow one, we can see that I'm seeing a smile, I can see a dog, I can see a facial expression, I can see a couch. I don't know where the couch is, but maybe it's where like my dog is. But then what I did was I got all those images on the edge, and then I managed to send them to a machine learning algorithm to learn and to start detecting, label what it is that I see on an image, because that is also another ML task, that we can label what we see and the objects we see on an image. And it can be on a video because we process everything in the form of frames. But the idea of this algorithm is for really know how to learn in a collaborative way, and also to take the advantage of doing federated learning on the edge using not only, we don't need to use the full version of, for instance, TensorFlow. We can, if you're using TensorFlow, you can use PyTorch or other technologies. But I'm going to say about TensorFlow, which is the one I'm most familiar with. And you can export models as a TensorFlow Lite model, or even as a TensorFlow micro model that can run on embedded devices. So we can run those models on the edge, train, and instead of passing all that information down to a command center, we can then just pass the weights, and then the weights arrive, we can retrain our model, and we can identify the participants of the cohort so that we can propagate back the weights that the machine learning model should incorporate to start running and making better prediction. And we do this in an iterative way. iterative way so that we can learn as we see more things and as we start improving the models that we have. And this is a kind of some research areas and open questions that we have, that is like how we can personalize the algorithms and things to run on the edge, on vehicle personalization, how we to do more with less spacecrafts, how we can do faster model training or more resource optimized kind of machine learning training. And also to start seeing, like, can we save battery by training those models and maybe increase the lifespan of spacecraft? So there are many kind of things that we can think about. And how do we even create feeder models, like even with less data? But the idea here is like, it's an open research area, and any kind of interest you have is going to make a huge difference. And so there are many like open questions. And this is what I had to share with you guys today. Thank you so very much for having me here and for engaging with us on this conversation. I will hand it over to Vint and stop sharing my screen. Thank you, guys.
Thank you so much, Lara. God, that was amazing. Lara told me she could do this in half an hour, and I didn't believe her. So here we are. Very much. There are several questions in the Q&A, so why don't we start with those? Patrick Ryan asks, how much AI are you seeing on satellite, in other words, edge computing versus terrestrial AI, and what are the trends?
Well, I see people are moving. Is still like at the beginning? We don't have that many applications, but what I see is that people are starting to see, because some of the things we have to react at the time we see it. So think about, we are seeing like a phenomenon or something, and we wait until we download the data and do something. Wouldn't it be better for us to just see, oh, I can see something really difficult happening here, and just send an alert to Earth to go and see what that is happening? So we have a trend here. And what is driving this trend now of doing this edge computing is more like we are having more computer power, and these advancements on, for instance, the faster convolutional neural network, that we can just run algorithms much faster, and also federated learning, which is something that is really going to change the field, I see.
Now, I hope you're right. I'm going to come back with a question about federated learning, but let's go on with the questions that have already been asked. Ahmed asks, what is the most accurate cloud dataset server or servers for these classifications? I think I'm not sure what this question is, but I think he might be asking about the kind of servers that do best for this sort of classification. If I've got that wrong, Ahmed, and you're still with us, please type a elaboration into the Q&A. But to the extent that this question makes sense to you, Lara, do you want to try to respond?
Well, if that is about like the best environment for us to run those, I would say, for instance, that depends on the model you are trying to execute. So for instance, if you're running with tabular data, you might be okay with running things on big GPU, CPUs. But if you're running with like images and videos, you might need to use like GPUs, make use of GPUs, and also TPUs that is available for us to run, for instance, models based on TensorFlow, that we can optimize the mathematical calculations that we have in all those different neural networks, because that enables us to learn much more about the tiny things that are so invisible to the human eye. So I would say those, it depends on the model and the architecture that we have. But I would say for multimedia processing, like running on GPUs like minimum, and also running on kind of TPUs, are really like what is enabling us to run those types of models.
So now there are some other questions, but they go in a different direction. So I want to stay on the models and the generation of models for a moment. The federated learning is exciting because you can imagine multiple sources of information in many different places, and we're trying to build models that reflect the kind of information we're detecting. The question, though, is how to assemble the resulting models into something that's collectively useful, that's combined into a single model. There are some very simple ways of trying to combine the models, and they probably may or may not be the best way. So are there any current experiments to do the following? Run a federated experiment by training models with different data sets, and then combining the models, and perhaps in various and sundry ways, and comparing that with training a single model with all the data that came from all of the various sensors, by deliberately trying to compare the federated model with a model which we think is optimized based on all the data that was accumulated. Is anybody working on those comparisons?
Yes, so we see a lot of people, several researchers working in this area, because we have to understand how to best combine those results and what is going to be the operation that is going to be optimal to this. And not only how to combine, but also how to select the participants of the cohort. Because we might have some members of the cohort just adding more noise than signal, which is not going to be helpful at all. So we started federated learning with some simple models like naive combinations, that is just making a simple average, that is the federated averaging. But now we are having some techniques using Adam optimizer and some optimizers to make sure that we are actually combining them in a way that we preserve the best characteristics of those matrices, instead of just like making kind of a blind combination of them. So we see like research going into this field of analyzing who can participate in a cohort, what is the minimum requirement of model quality that someone has got to meet to really participate in this, and how we best combine those matrices. So I see research on moving away from naive kind of combination and adding more optimizers to the combination of those matrices of weights for the machine learning.
So one obvious thing to consider as people become more and more able to try some of these ideas out on various platforms, including ours at Google, you wonder whether there is a crowdsourcing opportunity here. Some of you on the call may know about another sister company called DeepMind, which is part of the Alphabet group. They did some very interesting work on the folding of proteins, and they got lots of help from people who would just experiment with trying to fold the proteins in various ways. And eventually they managed to train a machine learning system that learned from the various examples that the crowdsourcing provided, and recently reported that they had now folded some 200 million proteins that are understood to be potentially made by the human genome. So the question is whether there might be some sort of crowdsourcing experiment with the federation of models, and so letting people try various and sundry ways of combining the models to see what comes out as effective. And I think you implied in your talk, Lara, that the successful combining of models may depend a great deal on the kind of information that is being collected and then used to train the models, some of which might turn out to be distracting as opposed to contributing, because they're from the wrong space of source information. So I don't know whether we should be trying that out, but it's amazing some of the results that crowdsourcing have produced. Well, we've got an interesting and more legal question from Patrick. He says he's wondering whether the DoD laws are going to interfere with our ability to actually implement what you're describing. He says that AI that analyzes space data is sometimes dual use. In other words, it could be used for various military applications, in which case the International Trade and Arms Regulation and the CFIUS, which has to do with the financial engagement of non-US organizations. I know this is a very US-centric question, and the same argument, of course, could be raised in other countries as well. But this means that we're supposed to be careful about what kinds of data we use and how we share the resulting models. So collapsing Patrick's question a little bit, he's wondering whether the fact that a lot of Silicon Valley folks, including logical Silicon Valley, where you are in London, are not US citizens. So does that mean that only US citizens should be involved in developing AI for space? And I hope the answer is no, that it's largely open source. There's a great respect for scientific enterprise in an international and collaborative setting. But do you have any light to shed on that?
Yes, so that is a very interesting question. And that is one of the reasons that I started looking into federated learning and analytics. Because when we work with this type of architecture, let's call it this way, with this type of framework, you leave the data at the edge. You don't see the data. You don't see any PII information. You don't understand where that data comes from. You only see blind matrices. Of course, it's not bulletproof. However, think about another example, like in medicine. We have like rare diseases in some different parts of the world. but we have a lot of like privacy concerns. So we have like sovereignty and some other things about like where data should be located and how we share that data because of privacy concerns. So if you think about it, that for us to better create solutions for our medical systems, we should be able to bring those data sets together, because the tiny data sets isolated, they are not powerful enough to create good machine learning models, because we're not having a very good sample of data for us to analyze. So I think federated learning opens a door for us to be able to bring those data that are fragmented and they are on their own, they're not that powerful to train a machine learning model to create meaningful results. So I think that there's a lot of things for us to do in terms of federated learning to ensure the privacy and the trust. But the idea for federated learning emerged with this privacy first idea that we leave the data on the edge. We don't care about how the data looks like. And that kind of idea, that kind of a handshake that we just pass the matrices, we don't see where the data is, we have no idea who the user is, what helps us to build those better models that we have. So the sum of the parts are bigger than the parts alone. Does that make any sense? I think you're mute, Vint.
Yeah, it makes a lot of sense. And I'd like to suggest an interesting experiment that we could perform. Imagine that we have data scattered all over, and we run models. We develop models for each of those different data sets. They don't get transferred anywhere. They're wherever they are locally. But what we do is allow everybody to see the models, and we allow everybody to combine them in any way that they like. And then they take the combined model and run it against their data sets. So we can try to, and then we iterate so that we end up with everybody testing the combined model against their original data sets, and then we can try to get a sense for which of the various possible models do best in evaluating the data in each of the distinct and separate sources. So we never shared any data at all. We've only shared models, which is the essence of your message. Let's see, Jorge asks the question, have you run any tiny ML on Raspberry Pis?
Yes, I have kind of run many of them. So for instance, the AstroPi, that I have a collection of AstroPis, and I detected anomaly. So as you shake the AstroPi, and the AstroPi was taken to the International Space Station. So when you shake the AstroPi or do something like very severe movements with them, you can detect some types of anomaly. I also have done that with object detection. And the idea is that you train your model on a proper environment to process images and videos, like with convolutional neural network, and then you can export this in a tiny ML model that you can have and deploy that even on embedded devices, on watches. So I have a NanoPi that is kind of quite tiny, and I managed to run a micro model from TensorFlow just to detect kind of humidity and also the humidity of the soil. So I built like a board, a tiny, oh, is this one here? So a board that I can kind of, I don't think you can see because of the background, but I can put that on my plants and I can check whether that needs to be watered or whether that is at risk of something going bad with that. And the good thing about using a framework like TensorFlow or PyTorch or any other is that you can transform your models from very big ones that you have to run on big servers into tiny ones that are just perfect for you to run locally on the edge. So many of the models are optimized to be run on the edge. So I can give some pointers if any of you guys are interested in getting started.
Oh, thank you, Lara. Let's see. Ahmed is asking again, he says, what's the most accurate SAT satellite, I guess, as an interplanetary cloud server? He's asking, can we use the interplanetary file system? I'm going to start an answer to that, which is that the interplanetary file system is completely independent of the interplanetary internet at the moment. It just happens to share reference to the same term, interplanetary, but it is intended to be a highly distributed system. And what Lara is talking about in some sense is, especially with this federated learning, is in fact very much a highly distributed set of data which never comes together in any one common place. I don't know whether you want to add more to that with regard to which satellites could serve as interplanetary cloud servers. I think we don't have any yet that would qualify for that, unless you know about something I don't.
Not at the moment, but I agree with what you said before. But I think For that, we have to really understand a little bit more about the capacity and capabilities of each one of them. And maybe some of them, they can be the aggregator or the mid aggregator, or perform more kind of demanding tasks that other might not be able to. But that is kind of an evolving field, I think.
There was an image that you showed us earlier in your talk. It was a picture of a cyclone or a hurricane. And when I looked at it, it looked to me a lot like a galaxy. And so I wondered what would happen if we took that picture and presented it to your galaxy and star detection system. Would it tell us it's a galaxy, or would it say it isn't?
Yeah, I can do that experiment today and share the results with you guys, and put that at the end of my presentation so you can see that.
I'm sorry, everybody. I have an incoming annoying call that I can't shut off. So apologies for the extra noise. Patrick Ryan asks, will there be a Google for space data, so to speak, or will space data sources be siloed? In other words, will somebody be assembling all the data into one place? And I don't have a good answer to that, but maybe Lara does.
I think that is one of the things that we have to work together with those people generating and collecting data in space. So for instance, we have to understand how the data is collected, understand the quality, come with some standards for us to understand the meaning of the data that we are collecting, so we can classify them and put them together if they are trying to explain the same phenomena. And so there's an area that we can kind of create a data marketplace for space data, where NASA, ESA, and all JAXA and all other participants collecting data, they can kind of put it there, and data that is checked for quality, and that we have like some standards to understand the relevance of the data, the context of the data, and what each data set might mean. Which is funny, I was in a talk ages ago, and I remember a guy saying that standards, they're like toothbrush. Everybody has its own, but no one wants to use each other's. And coming up with a standard to define the data is something that we might also need, so that we can understand the meaning and understand the quality, how the data was acquired, all those kind of techniques, so that we can create and do better feature selection and better kind of image selection and video selection for the problem you're trying to solve.
So we have one last question from Samo Grasic, who says, thank you for your inspiring talk. Is there an available image compression algorithm or software that could be used on the DTN Edge point or the rovers with a high compression rate, tailor-made for AI image recognition, and is it able to preserve and extract crucial image features that are needed for AI training? So compression scheme and AI training, do they conflict, or can they be mutually reinforcing?
Yeah, so what I would recommend you to do is to look for like frameworks, for instance, like TensorFlow, PyTorch, and some other kind of frameworks that are supported by those big frameworks that will allow you to compress the image, but preserve what is interesting in the image, because you don't want to lose all the signal that is on the image. So I know like in TensorFlow, we have the TensorFlow compression library, and that offers a lot of like data compression tools. We also have like more specialized software. We have like in MATLAB, we have image processing toolbox. We also have, so for instance, we also have OpenCV, that is like an open source computer vision library, and they offer hundreds of machine learning and computer vision algorithms, and they offer like thousands of functions to support like compressing the data in a way that you can define, no, that is too much compression, I'm kind of losing all the information that I need on that data. So I would recommend like looking for OpenCV, TensorFlow, MATLAB, and also looking for, there's a project on GitHub, I think that is called High Fidelity Generative Image Compression. And it's on GitHub, you can check it out, and you can also contribute with code. But that one uses a lot of techniques from machine learning models to use AI to compress the image in a way that you don't lose signal that you might need.
Thank you so much, Lara. We are out of time, basically. So thank you all for joining us. I hope that those of you who may have joined us without being members of IPNSIG will consider joining us. As you can see, there are a lot of us scattered around the world, more or less uniformly. We're very proud of the fact that we are an egalitarian special interest group and chapter of the Internet Society. So once again, many thanks to you, Lara, and to all of you for joining us in this Academy session. We look forward to seeing you once again on the net. Meanwhile, bye for now.
Thank you, guys. Bye-bye.